this is Dr. Kruse, Elementary Statistics. We're going to solve some probability word problems. Let's just back up a little bit. I want to remind you that, mu, the population average or the population mean, is never really known. It's just too hard to calculate. It's something that we guess at by taking samples of, a reasonable size, and we call those samples x bar. So mu is the true number, the true average, the true mean that is out there, but it's just kind of impossible to calculate. So, for example, maybe in the world there are 546,179,483 Black Angus cows. I just kind of made that up. All right, pretend that I could weigh them all at the same instant, before any cows are born, before any cows die, at the same instant, their instantaneous weight. Let's pretend I could put them all on a scale, all the cows in the world, all the Black Angus cows in the world, and maybe they weighed 546, 546,179,483 pounds. That's what my scale said. And I want to average this, so I'm going to divide by the number of cows, which was this number here, 546,179,483 cows, and I come up with an average of about 1,000 pounds per cow. Well, if I could do this, if I could actually get an instantaneous weight of 546 million cows and divide it and average it, if that was even possible, well, then that would be mu, all right? That would be mu. That number is out there. It's just impossible for your average human to calculate. It's just kind of impossible to do. But what can I do? Well, I can just go in my pasture and catch 30 cows, 30 Black Angus cows. I can weigh them. I can run them across the scale. That's not that difficult. And maybe my cows weigh 29,880 pounds, and I divide that by 30 to get an average. So maybe my cows weigh about 996 pounds per cow. So my X bar is 996. This is a real number that I can calculate. It's pretty close, to mu. It's not bad, but it's not going to be exactly mu. Our X bars are going to be off a little bit. All right, we're going to do the best that we can do, but the best that we can do is get close to mu. And maybe I weigh my neighbor's cows. Maybe my neighbor's cows are a little bit fatter. They weigh 30,120 pounds divided by the 30 cows that we could catch. And maybe that averages out to 1,004. So see, we're both relatively close to mu of 1,000, the true average. All right, we're both close, but we have to understand that when we're taking samples, it's just going to be close. So all we can really do in statistics is just take a bunch of samples, take some good samples, and make a pretty good guess at what mu is, at what the true population mean is. Here's just kind of a visual for you guys that are visual learners. In red here, I have a normal distribution curve, and the high point is above 1,000 pounds, which is mu. That's the true average, the true distribution curve. All right, which is impossible for us to calculate. All right, we can weigh my cows and get an average of 996. That would put the high point of my curve over here a little bit to the left. And maybe my neighbor's cows are a little bit bigger. Their average weight was 1,004. That puts the high point of his curve over here to the right. So both curves are, normally distributed, normally shaped, but they're just not quite what the true population mean is. All right, and let's just go over some terminology before we move on. If you're talking about the population, the average or the mean is called mu, and the standard deviation is lowercase sigma, standard deviation. If you're talking about the sample, the 30 cows that we could catch, well, that's called X bar for the average, for the mean. But for the sample, we usually use the lowercase s for the sample standard deviation. We're going to have to adjust our standard deviation calculation just a little bit. We have to adjust it for the small sample size, all right? Unless you're, weighing like 1 million cows or something like that, your sample's actually going to be kind of small. And to make your data more accurate, we have to make a tiny little adjustment by taking the population standard deviation, what's believed to be the standard deviation for the population, and we have to divide it, we have to adjust it by the square root of the sample size. All right, so maybe you have a standard deviation and you weighed 30 cows, you divide it by the square root of 30 and so on. This is also called standard error. Our Z conversion formula, where we converted an X number, your raw data, to a Z number, those 0, 1, 2, 3 numbers on your standard distribution curve, well, it usually looks like this if we're pretending that we know what mu and the standard deviation are for the population. But in reality, we're going to be dealing with samples, all right, the 30 cows that we could catch. And since we're doing our math, since we're doing our statistics on the sample, we have to include this little adjustment here down on the bottom. We can't divide by standard deviation. We have to actually divide by standard deviation divided by square root n. That's the same thing here. We're just writing it left to right. It's just easier to enter into the calculator. So standard deviation divided by square root of n. Standard deviation divided by square root of n. Same thing. I'm just writing it left to right in the denominator. This is also called variance, variability. It's going to vary less as your sample size gets bigger, as n increases. So 30 cows is fine, 300's better, 3,000's better than that, 30,000's better than that, and so on. All right. The more you measure, all right, the more you include in your sample, the less your data is going to vary. Central limit theorem basically says that 30 is the magic number in statistics. As your sample gets bigger, your sample distribution becomes normal, all right? If you just weigh like 1 cow or 2 cows or 3 cows, well, there's no telling what could happen, and you can't really draw a normal distribution curve. But they've noticed that as long as you take 30 measurements or 30 weights or 30 surveys or interview 30 people, as long as the number of data points is 30 or bigger, well, now we can assume that the sample distribution, the distribution shape of your sample will be normal. It will be in a normal curve shape. And this is just based on empirical study. That's a fancy word for, we just noticed that after observing a bunch of experiments and stuff. After we observed a whole bunch of those, we just noticed that as long as you take at least 30 measurements, your data will fall out into a normal distribution pattern. All right, there is some notation over here in the problems that I'm going to show you that's confusing, and I'm sorry, but this is the way they write it. This is the way I prefer to write your sample data. This is your sample average, x bar, and your sample standard deviation is s. And I showed you that little calculation just a minute ago for s. Population, as always, is mu and sigma. But, I prefer to use x bar and s for your sample data. And the problems I'm going to show you today, they're going to label x bar as the average, but for the sample. All right, the population mean, not the population, the mean for the sample. So this is a hard way of saying the sample mean and the sample standard deviation. I'd rather they use these letters here, but they don't. You just have to get used to their notation. So it is the average or the mean, but for the sample, and the standard deviation for the sample. So starting with this problem here, which is a pretty simple word problem. We don't really have a story up here in the sentence. We're just given that the population average is believed to be 20 and the standard deviation is believed to be 14. So we believe that, I'm just going to make up my own story. We believe that these bags of cookies weigh 20 ounces, give or take 14 ounces either way. All right, so if a random sample of size 47 is drawn, so our n is going to be 47 when we're doing that little standard deviation calculation, find the mean of the sample, the average of the sample, find the standard deviation of the sample, and then find the probability that your sample falls between 20 and 22. Find the probability that your sample average, all right, we took 49 bags of cookies. I'm just going to go with my story here. So on the package of cookies, it's labeled that there are 20 ounces inside this bag, 20 ounces of cookies inside this bag. That's what's believed to be in there. Well, I went and bought 47 bags of cookies, and I weighed them and divided by 47, and I'm going to come up with an x bar. Now, what's the probability that my sample, that my average of those 47 bags of cookies, what's the probability that my average is between 20 ounces and 22 ounces? All right. For the purpose of this problem here, the average or the mean of the sample is going to be the same as the population mean. Now the standard deviation, we're going to have to do that little calculation. We can't use the population standard deviation of 14. We have to divide it by the square root of n, and I'll show you that in a second. And then we're going to calculate this probability and hopefully wind up at, about a 34% chance that our sample average will land between 20 and 22 ounces. All right, so the first thing I like to do, we're starting the problem right here. First thing I like to do is I like to list how many I have, and then my population data, my population mean and my population standard deviation. And then I usually do the same thing for the sample. Now I would usually use X bar and S over here. You can write that in if you want to. So X bar and S, but this is the notation that the problem is using. So I'd want to know the average of my sample, and I'd want to know the standard deviation of my sample. So the first question they asked is, okay, what's the average or the mean of your sample? Well, for the purposes of this problem, we're just going to make it the same as what's advertised on the package. We're just going to say we weighed our 47 bags, and voila, it landed at 20 or whatever. And the standard deviation, I can't use the population standard deviation. I have to divide it by the square root of how many samples I drew, how many bags of cookies I weighed, the square root of n, and that's where that 2.04 comes from. So for my sample, I'm going to say the average weight was 20 ounces or whatever, with a standard deviation of 2.04 either way. All right, now for the probability part of that problem, we wanted the probability that the average weight of my sample is between 20 ounces and 22 ounces. All right, so X values do us no good. X values are your raw numbers, all right, your story problem numbers. I can't use my Z table unless I convert these X numbers into Z numbers, those 0, 1, 2, 3 numbers that I look up in the Z table. So I'm going to go ahead and convert my X numbers to Z numbers, and I'm just going to use a version of that little Z conversion formula that I showed you just a minute ago. I'm going to convert 20 to a Z number. I'm going to put 20 right there, and the other 3 numbers were given. We'll calculate that in a second. And then my X value over here is 22 ounces. That's my raw data, and the other 3 numbers were given. All right, so let's move down here to this calculation. I'm going to do my raw value of my raw data of 20 minus the population mean of 20 over the standard deviation 14, which I have to adjust by dividing by the square root of n, 47. We make the same calculation over here. It's just our X will be 20 instead of 22. Oh, I said that backwards. My X will be 22 instead of 20. Over here, my X value was 20 ounces. Over here, my X value is 22 ounces. I'm going to convert both of those. This winds up being 0. This winds up being 0.98. So now I have my Z numbers, those 0, 1, 2, 3 numbers that I can look up in my Z table. So I'm looking at the probability that Z is between 0 and 0.98. Let's start over real quick. The question said, what's the probability that you weighed those 47 bags and got an average weight, and that average weight is between 20 ounces and 22 ounces? Well, I changed those X numbers to 0 and 0.98. So in my Z table, I'm going to look up what's the probability Z falls between 0 and 0.98. Come over here to this visual here. So here's 0, right smack dab in the middle of my normal curve. 0.98 is almost 1. That's almost 1 step to the right. All right, so I'm talking about basically 0 to 1, and I want the area in between. Now, how do I find that? Well, what most people do is they look up Z equals 0.98 in the Z table, and that's going to tell them what percentage of the curve is to the left. Let's look that up real quick. We're going to look up 0.98 in the Z table. All right, so 0.98, I'm in my Z column here. Here's point, and I go over to 8. So that's 0.98 right here, 0.8365. That says 0.8365% of the curve is to the left. Or if you talk about people, that's about 84 people live to the left of 0.98. Now that's too many people. I don't want all of those people because some of these people over here I don't want. So where I'm at so far is I looked up 0.98 in the table and it told me from here all the way to left infinity was about 84% of the curve. Or if you want to talk people, about 84 people live from here to left infinity. Now I just want the people living in here, all right? I don't want these guys in the white area. So the next thing I do is I look up this number on the left in the z table. And if you'll look up if you look up 0 in the z table, it'll tell you, well, 50% of the curve is to the left. That kind of makes sense. 0's in the middle. That means 50's left and 50's right. So if I look up 0 in the z table, it says, hey, 50% of the curve is to the left. Or if we go back to our people analogy, 50 people live in the white area. So to start over, if I look up 0.98, it tells me about 84 people live from here to left infinity. But I don't want these 50 guys living in the white area, so I'm going to subtract out the 50 guys. All right, here's our math over here. There's 0.8365 from 0.98 all the way to left infinity, but I don't want the people in the white area, so I subtract them away from the 0.8365, which leaves 0.3365 here in the middle. One more time, there's 84 people living here, but I don't want the 50 people living here, so I subtract those 50 from 84, and I get 0.3365. Here's the notation right here. Look up the people to the left of 0.98, and then subtract the people to the left of 0. All right, let's look at the next one. Now, this is an actual word problem. Let's go ahead and read it together. Coal is carried from a mine in West Virginia to a power plant in New York in hopper cars on a long train. Those are just those big cars that look like boxes that hold a bunch of coal. You've probably seen them going down the railroad, taking coal to a power plant. And these power plants, they don't really buy it like by the pound or anything. They just buy coal by the carload. All right, they just buy it in bulk. So they just say, send me 100 cars of coal or whatever. Now something loads those cars with coal, and it's just, they call it an automatic hopper car loader. So it's going to load those railroad cars with coal, and it's calibrated. It's set. It's supposed to put 61 tons of coal in each car. So this is going to be our mu, what we assume to be true. All right, it's kind of like the advertised weight on a bag of cookies or the advertised number of ounces in a bottle of pop. This is what is believed to be true. This is the advertised claim. That's going to be mu. This is what they claim is happening. And basically in statistics, our job is always to challenge this claim. All right, we need to test it and see if maybe they're putting a little less in, or maybe they're putting too much in, or so on. But later on, we're going to frame that challenge as a hypothesis test. The actual weights of coal loaded into each car are normally distributed. That's something they have to tell us so we can use our normal distribution curve and our formulas, with an average or a mean of 61 tons and a standard deviation of 1.2 tons. So they're saying, hey, we're going to put 61 tons on average into these cars, give or take 1.2 tons. That kind of means that, one car could be a ton light, but the next car might be a ton heavy, but it all averages out to 61 tons per car. That's kind of what that means. What's the probability that a single car, one car, chosen at random will have less than 60.5? So one car, that's a single car load, n equals 1. So what's the chance you weigh one car and, it's supposed to have 61 tons in it. That's what they told us. What's the chance you weigh one car and it has less than 60.5 tons? So it's a little bit light. We're going to calculate that probability. Hopefully we wind up here. And then next question, what's the probability that, okay, now you're going to weigh 25 cars. Maybe there's 100 cars sitting on the track and you're just going to randomly choose 25 cars to weigh. So you're going to weigh those 25 cars, you're going to add up that weight, divide by 25, and you're going to have a mean or an average weight. which you're going to call X bar. That's your sample. What's the probability that your sample of 25 cars winds up being less than 60.5 tons? You add the weight up of these 25 cars, you divide by 25, and you get an average weight that's lower than 60.5. Well, that could be a problem, because if 25 cars are running light, that's a problem, and the loader needs to be adjusted. It's probably out of calibration. All right, let's get started on that. All right, so the basic question is the automatic hopper car loader, is the loader out of whack, out of calibration? All right, we're testing it. They're claiming that this thing loads the cars with 61 tons of coal on average, and we're testing it to see if it's out of whack, to see if it's loading them light. All right, maybe we don't trust these guys, and we want to make sure that they're putting 61 tons of coal in the car, so we're testing it. Now the first one says, let's just sample one car. What's the probability we weigh one car and it comes up light? So I like to put N first. N is 1, and then my population data. So the population average is believed to be 61 tons per car with a standard deviation of 1.2 tons. Now in this case, we were not given any sample data, but we can work the problem without that. So probability that we weigh a single car and it comes up light, specifically less than 60.5 tons. So the probability that X, our weight, is less than 60.5 tons. Well, I can't use these big numbers here in the Z table. I got to convert my X numbers to Z numbers. So let's convert X to Z. Here's my formula. My X is my raw data number, 60.5, and the rest is given. That's going to be minus 61 over 1.2 divided by the square root of 1, because we're just weighing a single car. So here's your substitution. This is X. Mu was given, standard deviation was given, and we have to adjust it for the small sample size by doing this little calculation here. So the probability that X is less than 60.5 is the same thing as the probability that Z is less than negative 0.42. Okay, this is a number I can look up in the Z table. So I grab my Z table that's over here a little bit left of 0. So you're going to be on the negative side of the Z table. And you're going to look up negative 0.42, and it's going to tell you the area to the left. It's going to tell you this shaded area right here, which is about 0.3372. That's about 34% of the curve. So this is about 34%. All right. So what's our conclusion? Our conclusion is, well, there's about a 34% chance, that's about 34, there's about a 34% chance that I'll weigh a single car, just one car, and it comes up light. And basically that just happens, all right? If you just pick a random car, they're not going to be right at 61 tons. It's impossible. Remember, mu is just kind of impossible to hit right on. One lump of coal could throw it off a little heavy or a little light. So some of those railroad cars are a little light and some of those railroad cars are a little heavy. But hopefully, if you average out a whole bunch of cars, they'll come up at 61 tons of coal per car. So it's no big deal if one car is a little bit light. There was a 34% chance that was going to happen anyway. All right. It was kind of expected that one car would be a little light, or even one car will be a little heavy. But we were calculating the probability that a single car comes up light, and it worked out to pretty high. We had about a 34% chance that a single car would come up light. So if a single car comes up light, that was a pretty high probability. That was probably going to happen anyway. We're not going to panic yet. We're not going to accuse anybody of cheating us or loading the cars light yet. Okay, but what about 25 cars? If I randomly select 25 cars and add up the weights and divide by 25, and that comes up light, what's the probability that would happen? All right, organize your data. We're going to weigh 25 cars. It's believed to be 61 tons of coal in each car. That's the advertised claim. All right, what we believe to be true with a standard deviation of 1.2. Again, we don't have the sample data, but we're going to work it without it. So the question is basically, what's the probability that I weigh 25 cars and the average weight of all 25 are too light? All right, that shouldn't happen. So what's the probability that x is less than 60.5? That's the same probability. We're just weighing more cars. Change x to z, all right? So 60.5 is going to go in for x. 61 is going to go in for mu, 1.2 for standard deviation, but this time your n is going to be 25 instead of 1 because we're weighing 25 cars instead of a single car. So here's your substitution. It works out to the probability that z is less than negative 2.08. So the probability that I weigh 25 cars and the average is less than 60.5 tons is the same thing as saying the probability that z is less than negative 2.08. Well, if you look over here at the sketch, that's more than 2 steps to the left. Gosh, we're almost out here in outlier area. You know, if you go about 2.5 steps, you're in the really unusual area. So we're almost to the outlier area. And we look up z in the table, and it tells us the area to the left of negative 2.08 is only 0.0188. If I move that decimal 2 to the right, that's 1.88%. That's pretty close to 2%. So there's only a 2% chance that you weigh 25 cars and the average weight of all 25 comes up light. All right. So let's draw a conclusion here. There was only a 2% chance that I'll weigh 25 cars and I'll come up light. So if that happens, if you weigh 25 cars and the average weight comes up below 60.5, well, now it's a big deal. Now you need to talk to these guys and say, hey, you guys are shorting us on the coal. I weighed 25 cars. The average weight was less than 60.5 tons. There was only a 2% chance of that happening. So now I'm positive that your hopper car loader is out of adjustment. It's loading the cars too light. So you guys need to go fix that. And then for our final word, sorry, I can't talk. For our final word problem, it says let x be a random variable that represents the level of glucose in the blood. All right, so x is measuring the level of your glucose after a 12-hour fast. Okay, that's what you usually do when you measure, when you draw blood, they tell you to fast for 12 hours before they take it. So x is going to measure how much glucose is in your blood. Now assume that for people under 50 years old, x has a distribution that is approximately normal. That's just some blah blah that they have to tell us. They have to tell us that the distribution is approximately normal so that we can use our formulas and so that we can use the z-table and use the normal distribution curve. So suppose that x is normal with a mean of 76. That means it's believed that a normal human has a level of 76. So it's believed to be 76 is normal. The average level of glucose in a person's blood is believed to be 76 with a standard deviation of 33. All right, so give or take 33. If you have a test result less than 40, remember it's believed to be that 76 is normal, but if your test comes up lower than 40, that's kind of an indication that you're producing too much insulin, severe excess insulin, and that you need some medication. Medication is usually prescribed. All right, so what we're going to do is we're going to calculate the probability that the doctor draws your blood a single time and that you come up low, that your glucose level is less than 40. All right, and then suppose the doctor takes 2 tests a week apart, because this is what they usually do. If it comes up low, they don't panic. They say, come back in a week and let's check it again. And then maybe they'll check it a 3rd week, and a 4th week, and a 5th week. And then maybe after you've taken 3 or 4 or 5 tests, well then maybe, if they're all low, then maybe the doctor will put you on some medication. But they're not going to panic over a single test. And we'll see why in just a second. So next they're going to take 2 tests. What's the probability that the average of 2 tests is below 40? And then they'll take 3 tests. And then they'll take 5 tests. And hopefully we can come up with these answers here. All right, so remember the idea. If x is less than 40, if the level of your glucose is below 40, that means you have too much insulin. That's bad. So just kind of keep the idea in your head, what we're measuring. First, we're just going to take a single test. You walk into the doctor's office and he pulls some blood and he tests it, and maybe you come up low. What's the probability that you'll walk into the doctor's office the first time and your glucose level is less than 40? Label your population data. It's believed that 76 is a normal level of glucose with a standard deviation of 33. Again, we don't have the sample data, but we're going to work it without it. So the probability that you go in a single time and your test comes up lower than 40, the level of glucose comes up lower than 40. I can't use raw data in the Z table. I got to change these numbers to Z numbers so I can look them up in the Z table. So let's convert X to Z. Let's convert 40 to a Z number, to a 0, 1, 2, 3 number. 40 goes right there with the X. Mu is 76. Standard deviation is 33. How many tests are we doing? Just a single test. This is the first time you walked into the doctor's office. There's your substitution. Z is less than negative 1.09. So saying that X is less than 40 is the same thing as saying that Z is less than negative 1.09. So now I can look up this probability in the Z table. All right, I'm a little more than one step to the left, than one standard deviation to the left, and I look up negative 1.09 in the Z table, and it tells me over here to the left is 0.1379, or about 14% of the curve. So about 14 people live over here. About 14% of the curve is to the left of negative 1.09. All right, so what's that mean? It means there was a pretty good chance that was going to happen anyway. There's no need to panic over one test, over a single test, because basically 14% of the time somebody's going to test low. I mean, if you line up 100 people, there's a 14% chance, which means that 14 out of 100 will probably test low on any given day. All right, that could have happened. So no need to panic yet. There was a pretty good chance that that was going to happen anyway. Some people just walk in and test low on one day and then test normal on the next day. So the doctor says, well, I'm not going to panic because there was a 14% probability that you were going to test low anyway. Come back in a week and let's take a second test. All right, so now everything's the same, but N is 2. Same probability. What's the chance that both tests, if I average them together, what's the chance that both tests' average level is less than 40? Change it to a Z. Remember, the only thing that's going to change is N is now 2. So the probability that X is less than 40 is the same thing as the probability that Z is less than negative 1.54. So now, instead of just one standard deviation to the left, we're about 1.5 standard deviations to the left, which gives us a smaller area over here, which gives us a smaller probability. We look up negative 1.54 in the Z table, and it tells us to the left of that is 0.0618, which is now about a 6% chance. So our probability has gone down from 14% to 6%. There's only a 6% chance that you come in and take two tests, a week apart, and that the average of those tests is less than 40. There was only a 6% chance that that was going to happen. So now the doctor's going to kind of take notice, but they're not ready to prescribe medication yet. They're going to say, you know what, I don't want to put you on pills yet. Come back in a week. Let's take a third test. So we take a third test. Everything's the same except N becomes 3. And now I'm down to a Z of negative 1.89. So I was about one standard deviation to the left, and then I moved a little further to the left, and I was 1.5 standard deviations to the left, and now I'm almost 2 standard deviations to the left. I'm negative 1, negative 2. I'm just short of negative 2. So I'm 1.89 standard deviations to the left. What's to the left of that? What's the area to the left? About 0.204. That's only about a 3% chance. If I move that decimal 2 to the right, that's about a 3% chance that 3 tests would all come up low. All right, there was only a 3% chance of that happening. Now, depending on the doctor, they would say, okay, I gave you 3 tests a week apart. They were all low. There was only a 3% probability that was going to happen. I'm ready to put you on medication. But some doctors will wait. Maybe they're just being overly conservative, and maybe they'll make you come in and take 4 tests and take 5 tests. So maybe this doctor made you take 5 tests a week apart. You came in 5 different times, And he wants to know the probability that 5 tests, that the average glucose level of 5 tests, if you add them up and divide by 5, is less than 40. What's the probability that that could happen? Like 5 times in a row. Change it to z, and now we're all the way over to negative 2.44. That's almost 2.5 standard deviations to the left. And remember, 2.5 standard deviations to the left, that's outlier zone. That's highly unusual. That's unexpected. We look up negative 2.44 in the z table, and to the left of it is only 0.0073. If I move that decimal 2 to the right, I have 0.73%. That's not even 1%. So that's less than 1%. We're close enough to outlier zone to call this highly unusual, that you took 5 tests a week apart and we averaged those levels, and the average was less than 40. Since there was only less than a 1% chance that that could happen, well, now we're certain that this is so unusual. The probability of that happening was so low that now we have to put you on medication.